All right. I did start the recording, so you don't need to remind me of that. I want to get through the slides because the midterm opens up or should open up at the end of the class today. I may have made a mistake and it already opened up. Uh, that's to your advantage. Or I may have made a mistake and it doesn't open up at the end of class, in which case, I hope somebody will tell me right away that I pushed the wrong button on Brightspace. It's a new program for your faculty. I like it better than the old one for sure, but it has a learning curve. So anyway, we want to talk about the heating systems. This is part of your project for sure. And so you want to pay definite attention to that, but also you want to understand it for the, the midterm. So we have steam heating, and steam heating, we're not doing that in our project. But basically what we do is we take water, we boil it to create steam, and then we distribute that steam around our facility. In the process of changing the state of water to steam, it absorbs a great deal of heat. And as we distribute that steam around the facility, we convert it back from steam back into water. And again, it's a change of state. And remember that every time we have a change of state, that we either uh, grab and hold heat, absorb heat, or we expel it. And so when the steam is in the facility at the area that we want to expel it, we convert it from steam to water, change of state, and it expels the heat that's embedded in the steam. And then we do that over again when we convert that water back into steam, and it absorbs the heat, and then we distribute that steam around the facility. Where we want the heat, we convert it back into water, and it expels the heat. So the way that we characterize the different steam heating systems is the piping arrangement and the pressure, and how does the condensate get back to the boiler. So when we're talking about the condensate, we're talking about the steam that has been converted back into liquid, to water. That's the condensate. We have to get that back to the boiler. And how does it get back? It could come back in terms of gravity, or we could pump it back. And those are the characteristics. So if someone wants you to describe your steam heating system, these would be the three things that characteristics that you would want to explain to them. What is the piping arrangement? What is the operating pressure? And how does the condensate get back to the boiler? Gravity or a mechanical pump? So the piping arrangement, we have either a one pipe or a two pipe system. And the one pipe system, I have some illustration of that shortly in the slideshow here, but it feeds the terminal unit, and it also returns the condensate back to the boiler. That's a one pipe system. It's very rarely used in steam systems. And the two pipe system is that there's literally two different, unique, separate piping systems. One that provides the supply, and one that provides the return. So we need to supply that steam to the terminal units or the boilers, or I'm not the boilers, the radiators, or we have to return that from the terminal unit to the boiler to change its state again back in there. And then we have various operating pressures. And I think that for purposes of this class, since this isn't a class in certifying you as a boiler operator, we can just say that there's high, medium, and low pressure. They don't have to know the PSI. Just recognize that your operating system may have high pressure, medium pressure, or low pressure. And for purposes of this class, I think that's enough. So here's where we're looking at the one pipe system. We have a pipe that is I'm sorry, this may be a two pipe system. And what we have is we have one pipe that is the supply line and one pipe that is the return line. Okay, so it would be a two pipe system, meaning that one pipe is for supply, one pipe is for return. And so let's follow the course of the water or the steam rather. In the boiler, we have water. We change the state of that water from liquid to gas to steam. When that happens, the steam absorbs a great deal of the heat, and then we distribute that in a supply line to our terminal units. That's our radiator, or well, I think the radiator would be the fine proper terminology for that. And so we have the steam coming in. We have a valve here. The valve happens before the terminal unit so that we can turn the supply on or off. Basically, that's how we control the temperature, is with an
Uh,
on and
Is
off.
that a shut-off valve?
It is a shut-off valve,
Oh,
definitely.
okay.
You can turn the supply off if you don't need it. And basically, you would have a thermostat possibly somewhere that would turn this valve on or shut it down. So if you set the temperature for this particular space on your thermostat, when you've achieved that temperature, what would happen is that this valve would close. And then as you go outside of the range of the temperature, that would send a signal to this valve and it would open it up again. Or alternately, you might just have a valve in your space. And when the heat in that particular space becomes uncomfortable or comfortable enough, you might just go over and turn the valve off, which stops any steam from going into the terminal unit. But with the valve on, which it would make sense if you ask, if I were to ask you in an exam, where does the valve occur? You should be able to think about it. Well, the valve doesn't serve any purpose of stopping the steam if we've already converted it to water and therefore expelled all of the heat that is embedded in the steam. So it would make sense that the valve would be on the uh, input side, not the output side of the terminal unit. And then on the other side, we have a trap. And then now we're looking at what? We're looking at water coming back. The condensate is coming back to the boiler where it becomes steam again, and we send it back around. And this is a supply line, and as the units call for the valve, meaning that the valve is open, then the steam will come in here, be converted, change of state, steam, liquid, steam, water. When that change of state happens, it expels the heat, which is how we would uh, distribute the heat into our spaces. Boiler, supply line comes around, valve is open, goes to the terminal unit. At the terminal unit, the temperature of the steam is reduced. The steam changes state from steam to water or liquid. At that point, change of state, it's exhausting the heat that's embedded in the steam. Then we pass a trap and back to the boiler where we repeat that again and again and again. Some of the
What
advanced,
quick question? What does the trap do again?
what is what?
What does the trap do again?
Well, what does the trap do? It allows excess steam to
Oh,
escape
okay.
into the living space, okay?
All right.
And it allows the condensate to return back to the boiler free of steam. So we don't want the steam going back to the boiler. We want the steam to have been changed in state back to its liquid form so that we can exhaust the heat from it. So what is the purpose of the trap? Excellent question. It allows the excess steam to escape into the space, number one. And number two, it allows the condensate to return to the boiler free of steam. We don't want to send the steam back to the boiler. We want to send the liquid back to the boiler. All right. Now, some of the disadvantages of the steam system is what? Well, it's noisy. We have to treat the water. In other words, the water that we get from the municipality is not uh, free of contaminants that appear when we change it to steam. So we have to treat it. So that water that's coming in from the municipality will be treated chemically. And because we get corrosion and scaling on the inside of the pipes that carry the steam. It's also kind of difficult to control. It's basically on or off. You don't set the temperature of the steam. The steam is steam and water is water. So you're using it on or off. You're saying, yes, I want some steam to be supplied to this terminal unit, or with the valve turned off, you don't want it. It does give extra humidity into the space in the summertime. We don't want humidity in our space, but in the summertime, we aren't using the boiler either, are we? In the wintertime, the moisture level in the air is less, and sometimes we need to increase that level of moisture embedded in the air, and the steam will help us in order to do that. Now, the hot water system, that's what we're using in this project is a hot water system. And how do we characterize that? Well, again, piping arrangement. You can have one pipe that supplies and returns. You can have one pipe that supplies and another pipe that returns. You can have one pipe that supplies hot water, one pipe that supplies cold water, and one pipe that returns. Or you can have one pipe hot water, one pipe cold water, that's the supply. And then we can have in our return, we can have one pipe for cold water and one pipe for hot water return. I'll have some graphics of that, which will make more sense. But basically, we count the number of unique pipes purposes, and that will tell us how many pipe system it is. In this class, you're required to do a one pipe system or greater. There's no extra credit for a two or a three or a four pipe system. Every year, I have students that do the four pipe system. And because for whatever reason, they're really interested in it, or it's not really that difficult to diagram, but there's no extra credit for that. So then how do we pressurize it? The method of pressurization. And finally, the operating temperature. What's the temperature? Those are the characteristics that you would use to describe a hot water system. And we have also what's called a series loop, which is unacceptable in your project. And yet I say this many times throughout the course, the semester, and I still see students at the end showing me a series loop system, which means no credit because that's an important component of your project. So I said one pipe system, two pipe system, three pipe, or four pipe. One pipe, it's supply and return only, one pipe. Two pipe system, supply and return, two different pipes. One takes the water, hot water to the terminal unit, and another pipe takes it back to a separate pipe takes it back. Three pipe, we've got chilled water. You might use that in the summertime to cool the spaces. And it has a hot water. Both of those are supply lines going to the terminal unit. And then on a three pipe system, we'll have one pipe that returns that back to the boiler or the chiller. And a four-pipe system was broken it down into two and two. Two supplies, two returns. What are in the supplies? Chilled water, hot water. What are in the return? Chilled water, hot water. So that's the different types of piping arrangements. In this class, one pipe is the minimum that you can do. A series loop system is not acceptable. We'll talk about the graphics of that, which I think will show a better illustration. And so hopefully you'll understand it a little bit better if in fact you don't understand it right now. How do we pressurize it? We have an elevated tank. We have a mechanical pump. We use steam to pressurize it, or we have an expansion tank. Those are some of the methods of pressurization for a hot water system. So operating temperatures, we said, again, I don't need you to memorize what the range of temperatures are, but recognize that there really is a high, medium, and low, just like the three bears, just right, not good enough, too good, whatever three components are. We've got high, medium, and low temperatures. And I think that's adequate enough for you to understand that there could be different temperatures. If your system requires just water for showering, dishwashing, then you would probably have a low temperature system, which would be 180 degrees. All right. But what you might have some sort of equipment that requires a higher temperature in your system, and that might be a medium temperature, or you might have this incredibly high temperature requirements. And that's why for your facility, you might have a high temperature requirement. That's why you would get to these really high temperatures. But for our project, our final project, our house that we're designing, we're looking at 180 to 250 degrees. So the only reason that that's important, other than probably an exam question or what are the operating temperatures, I certainly won't expect you to memorize any numerical answer to that. But if I said name the three ranges of operating temperature and you said high, medium, and low, I think that would be a very good answer. But as you're selecting your terminal units, the manufacturer might tell you how many BTUs you can expect to extract from that terminal unit based upon the temperature of your system. So obviously, if you have a high temperature system, in other words, the water that's going through your facility, being distributed through your facility is 400 to 450 degrees, then you're going to be able to extract a tremendous amount more BTUs from that water than if it's just 180 to 250 degrees. So you may need to pay attention to the manufacturer. They might have a terminal unit, that's your radiator, that operates three different choices operating under these three different temperature ranges. So pick the low temperature range, which is 180 to 250, and use that number to extract that the manufacturer claims that their unit will allow you to extract and distribute into the spaces. So now if we take a look at that over as opposed to steam, or if we're comparing it to steam, well, we can definitely control the temperature of the water, can't we? So we can turn the temperature of the water up, or we can turn it down depending on what the requirements are. When we say load requirements, that's the load on your system, your heating system. Also, hot water responds more quickly to load changes, all right? So that's a possibility or a benefit as well. We can balance the system easier, and these are all with comparisons to steam. We can control the flow rate easier. We can maintain a specific flow rate. Hot water systems are also quieter. We don't really hear anything in a hot water system. And it's a simpler installation, and the equipment is less demanding or expensive. So let's take a look at this. Now, this is the series loop. This is, imagine that each one of these terminal units are in a room in your facility, in your project now, which is the house. We have a boiler. We're going to have a supply pipe that goes right through the terminal unit. Now, if it does that, then what's happening is that water, the temperature of that water is going to be extracted to heat the space that it's in. And the water that comes out the other side, obviously, will be less of a temperature, which means that the water that goes into this terminal unit is at a lower temperature than the water in this pipe, this side of the pipe supply, the supply line, because we've extracted heat from it in order to heat this room. So it's 120 degrees here. We take, the temperature, we lower it down to 110. That means we have less BTUs available to us in order to extract, if we wanted to, from here. And again, think about it, the same is going to happen once we get onto this side. The water temperature will be lower, again, because we've extracted heat from the water. And that can go around and around and around until we get to this last one, which we may find that there's not a lot of heat or warmth in the water remaining. And so we don't have a lot of heat in order to be able to extract a lot of heat from that temperature. So this is a series loop system, and it is unacceptable. If you diagram your piping arrangement in this method, I'll stop looking at your project right there. I won't look at it anymore. Series loop is not acceptable. What are the disadvantages of a series loop system? Well, it's limited to very small operations. Its volume is limited by the size of the tubes, okay? The temperature drops, we just talked about that. The temperature drops rapidly across the path. Every time you extract heat from it in order to distribute that heat into your facility, the temperature drops on the opposite side of the terminal unit. So you have less ability to extract heat from there. And another big one, if this unit fails, you're done. Everything doesn't work. So you can think of this as when I was a child, and I'm 71 years old, so that was a long time ago, but we did have Christmas trees in our home, a Christmas tree, and the Christmas tree had lights on it that if one of the lights failed, all of the lights failed. And there was a string of, hundreds of lights that wrapped around the tree. And if one failed, they all failed because it was a series system. And this is the same. If this one fails, then the rest of the system has failed, or will fail as well. So there's some very serious disadvantages to that, but it has a low installation cost. All right. So low upfront cost, some disadvantages down the road. So this is not the most desirable methodology. But let's take a look at the next one, which would be a one-pipe system. Now that's okay for your project. It's very similar in that we still have one supply pipe, that's your one-pipe system, but we are extracting from that a valve, our terminal unit, and then this is simply a T that brings it back to the flow. So this hot water is always circulating around here, and we're extracting the hot water and running it through the terminal unit where we are then pulling off the heat from the system. So this is 100% acceptable as a piping system in your project. So let's assume this red line, real quick, ugly, quick sketch, poorly executed, is the house. And each one of these boxes represent a room in your house. Then that's exactly how the system would work. You'd run your piping system through there. That's your supply line. And then you will draw off of that supply line in the method and location that you choose inside of each of the rooms inside of your final project. So we have a one pipe system. Now, if we go to a two-pipe system, that's simply one pipe is a supply line in red, and one pipe is a return line in blue. So the blue would be the cooler water. The advantage of that is that we never take the cooler water, because remember, let's follow it around. Let's say 120 degrees here, we pull it through the terminal unit and it becomes 110 degrees. Where on the one pipe system, we dump that 110-degree water back into the 120-degree water. But in this system, we don't dump it back, so we never dilute the temperature down. We send that all the way back to the boiler. So supply line, extract it, and then the return line is a second unique and separate line. Water, let's continue this piping it around here. We have an extraction here. Once we've extracted the heat through the terminal unit, we return that water not to the supply line because it dilutes the temperature or diminishes the temperature. We have a separate line, which is our return line. So we have a more efficient system because we're not dumping the cooler water into the warmer water supply line. This is totally acceptable as well for you in your project, but it's not required, and there's no extra credit for doing a two-pipe system. So let's think about, well, here's a very horrible sketch, and remember that I said you are not graded on your graphic skills. You're not architects. I'm not going to hold you to that graphic standard. Architects should be a little bit better. But let's take a look. Let's assume that this is the wall. No, this is a supply line, and this is a return line. And we have a radiator. This is the wall here. We have a radiator, so we're coming off of the supply line, extracting the heat, and then dumping that back into a return line. That is as graphically necessary to satisfy my understanding of your to understand, for me to understand that you understand how to pipe the system. I don't need anything more elaborate than that, although most students do a nicer job using AutoCAD or Revit, or you can even do it in PowerPoint. You have that ability to do it, and that's fine, but there's no extra credit for a beautiful.
Hey, Professor,
Yes.
do you have to show flow direction on that, or is it just as long as you notate supply and return?
I
It's all
would
right.
say that no, the flow is would be pretty obvious to me. Now you can see that the wall is here. In this example, the wall is here. Normally, your supply line and your return line is either going to be mounted on the wall, on the inside of the wall, or in the wall. If you draw it that way, it would be difficult for me it would be difficult for you to communicate to me that you understand how to pipe the system. So what I'm asking you to do, it's conceptual. You can show your supply and your return lines outside of the walls or inside of the walls. Either way, this is the inside space. This is your terminal unit. This is your piping. And I know that you are not suggesting that the pipes be put in the middle of the room. It is simply a conceptual design showing how it would work. If you were to show this kind of a sketch to a plumber, they wouldn't put the piping in the middle of the room. They would understand that it needs to be placed inside or on top of the walls. It's quite often that the pipes run across the wall. Sometimes it runs in the floor. Sometimes it runs in the wall. In any event, for this class, its schematic is fine. Just show me how you're getting the hot water from the supply line to the terminal unit, and how are you getting, now this is a two-pipe system, how are you getting the return water back to the boiler. And that's very acceptable method in order to display the requirements of the project. You're going to determine how many linear feet of terminal unit you need, and then you'll tell me right out there, I need 10 feet of terminal units, right there, 10 feet of terminal unit. That would be 100% acceptable to me for this class. In real life, you'd probably want to do a nicer or a much nicer diagram, but for conveying to me, because that's what I'm looking for. And that's what we're looking for when your professors give you exams, is we're trying to see, did you understand the material? Do you understand the material? Did you read the material? Did you follow along in class? And that's what we're looking for, is for you to convey back to us, yes, you did. You understood it. You read the assignments. You've done the work. And that's what this method will do. Either have your supply line or your supply and return line, or your two supply lines and your two return lines on the outside of the wall, or show it on the inside of the wall. Either way, for me, is acceptable. It's absolutely acceptable for that. Now, obviously, this is a much nicer diagram. This was drawn by Dr. Edwards using PowerPoint. So that's a very nice, very simple way to do it. If you're not comfortable with your AutoCAD skills or your Revit skills, hand drawing is 100% acceptable to me. So here we have another one where I'm showing my supply line. I'm showing the wall, which is very rough here, but I've given you the blank floor plans that you can reproduce and draw your diagrams in there. But I have a return line, I have a supply line, and you can see that the terminal unit is extracting heat from the supply line and extracting the heat from that, and then the return is back to another pipe, which is the return pipe. But that's a two-pipe system. Then we have a three-pipe system. If you think about that, well, how many pipes are there? Well, there's three. And what do we have? Well, now we have a boiler and a chiller. One pipe that supplies our terminal unit is a cold or chilled water. One pipe that supplies our terminal unit is a hot water. Okay, so the hot water comes from the boiler. The cold water comes from the chiller. We have valves here to control how much hot water or how much chilled water goes into the terminal unit, and then we extract that cool or heat from the terminal unit and distribute that into the space. So a three-pipe system has what? It has one supply for chilled, one supply for hot, and then we have a return pipe that the water is sent back to the heating or cooling or chilling source. One return, two supplies. The two supplies are hot and chilled water. The return is a combination. Both of the output from each terminal unit goes back into a return pipe. And so when we get to the last, which is what? The four-pipe system, now we have two pipes to supply chilled and hot water, and two pipes to return chilled and hot water. And the difference is, if you go back and take a look at here, really what happens is we're dumping possibly hot water into the return pipe as well as chilled water into the return pipe. And you think about it, well, what would be an example where that could happen? And the example could be that this could be a north-facing part of the building. So you might need, you might be calling for hot water in order to heat that space, while over here, this might be the south-facing rooms in a building. And the sun may be coming in and heating up that space so severely that you actually might need chilled water. You need to cool that space down. So it's possible that you have the need for both chilled and hot water at the same time. But what happens is you're dumping the output, whether it's hot or chilled water, you're dumping it back into a return. This might be dumping cool water from the chilled pipe, and this might be dumping hot water from the hot pipe, but it's all both going back in there. So you're not only heating up that return water by the residual or the remaining amount of heat in the water, but you're also cooling it down. Then you get it to a splitter, and you split that water to the boiler and to the chiller. And so you need to heat the water up more, and you need to chill the water down more in order for it to go back into the cycle again. Whereas in this system, the chilled water always gets dumped into a chill water return, and the hot water always gets dumped into a hot water return. The hot water comes back right to the boiler. The chilled water comes back right to the chiller. And what do we have? 4-pipe system. Okay. And that would be obviously the most expensive, because if you think about it, now we have 4 pipes and we have to pay for the material, but you also have labor involved in the assembly or the installation of those pipes, and that costs money too. So obviously this would be the most expensive system, but it may turn out to be the most efficient as well, because your chilled water is not being dumped into the warm water. It's changing the temperature of that, and then you're going and sending that water back to the heating element, which is the boiler, and you have to heat that water back up. Your delta T is different because you're dumping chilled water into that, reducing the temperature down. That's the incoming, and then the output has to be 120 or greater. So what do you have? You have a larger delta T, which means you're going to put more energy into that system in order to raise the temperature back up again. So pause here because this is a critical portion of your project. I'll pause here for a second just to ask if that does in fact make sense to you. Or if you have some questions. Go ahead. Nobody has any questions at all? You understand this so thoroughly?
So, Professor,
Yes.
okay, so I wasn't here from the very beginning of the class, but my understanding of what you're saying is that we would choose a pipe system, right?
Yes.
1, 2, or 3. No,
Yes.
we're not changing the series. We're not using the series
Right.
because of the way it's constructed. But we will choose one of these systems, and we will either draw it or have it done in AutoCAD into the plans that you've given us. That's a part of the grade,
Yes.
right? So we choose one of these, and I think that's what I'm understanding.
Yeah, I think you left out the 4-pipe system in your
The
example,
4-pipe.
but yes, the series
Yeah.
is unacceptable. The 1,
Mhm.
2, 3, or 4 is acceptable.
Mhm.
The recommended would be the 1-pipe. There's no extra credit for 2, 3, or 4-pipe system. As long as you understand it, that's fine with me. So yeah, you do the 1-pipe system, which is that's the 2-pipe. There's the 1-pipe.
Mhm.
We have a supply and return is the same pipe, but we branch off of it. This is what I'll be looking for, is that you're making sure to branch off of your supply line
Okay.
in order to heat your terminal unit. And
Okay.
this is what I see too many times. Every single class, I think, okay, I have satisfactorily and completely conveyed to my students that this piping arrangement is unacceptable. And every semester, I get students who submit this. And I don't know what more I can say or what more I can do. If you have any questions about it, like Lisa just did, this would be a great time to ask.
Okay.
All right.
Also,
So again, I go into the last laps of this class thinking that my students fully understand, that you all understand the requirements for the piping of your terminal units in your project. And the proof will, of course, be in the pudding, okay, in the final project when you submit it. I hope you're all understand it. All right, so then we know that the change of state is the magic that creates either the absorption of heat or the expulsion of heat. All right. And Mr. Carrier said, let's change the state, but not the liquid to solid. Let's change the pressure from high to low in order to get cooling in our facilities. And how do we do that? Well, let's follow this around real quickly. We have an expansion valve, and the expansion valve changes the pressurization from high pressure to low pressure. And then when we change from high to low, it becomes cool. And we run that across that cool gas. We run that across and then push a fan across it to get that cool air into our space. Then we continue that cool air. We change the state again from low pressure to high pressure. And what happens is it has a high, now it has a high temperature, and we take that high temperature and we run air across it and exhaust it, that high temperature, from the facility. We bring that high temperature gas back and use an expansion valve to make it low temperature again, and now it's cool. And we take and we extract the cool into our space. So we're changing the state, but we're not changing the volume or the composition of it from liquid to solid, or from solid to liquid to gas. We're changing the pressure of it. And when we change the pressure, again, it absorbs the heat and then it expels the heat. So what's happening here when we put this compressor in here is that it's absorbing all of the heat and putting it into this coil or this pipe, and we blow that heat outside and then bring that high pressure gas across the here until we change the temperature, or we change the pressure to a low pressure. We expand it, it's cool again, and then we can extract the coolness from that gas. The change in state in this case in air conditioning is in the pressure of the gas. And let's take a look at, well, let's take a look. Here we go. Okay, so this is a diagram of a cooling or a heating system. In this particular case, I think it's air. But if we follow the air from the outside to the inside, we would start out here with fresh air. This wall represents the outside, and this is the inside. So remember, we have to change the air. We have to exhaust the existing air from the space, throw it away, and then we have to bring in fresh air to replenish the air that we are exhausting. And so we bring in fresh air. We put a louver or some sort of a screening device to keep the birds and the insects and the animals out of the building. And then we have a damper which allows air to come in or not to come in. We have that damper is controlled, and we can bring air in or not bring air in. And once we decide we're bringing air in, we want to filter that air. So there's a filter there, which that air passes through the damper and then across the filter. Now, a filter is designed to grab and to hold particulates, the stuff in the air that we don't want coming into the building. The filter grabs it and holds it. And then the air comes across, and depending on what the system is calling for, we may be putting a heating coil, activating a heating coil, or we're activating a cooling coil, which the air would blow across, and it would raise or lower the temperature of that air to get it into our space. We might add humidity. In other words, the moisture content might not be acceptable to our comfort level. And so therefore we would, the outside air might not have enough humidity or moisture in it. So we might add some to it, or it might be the opposite. It might have too much humidity and we're going to take some out of it. We talked about how that can be done, removing the moisture from the air. Remember when we said that a given volume of air at a certain temperature can hold more or less water than in that same given volume of air at a different temperature. So the warmer the air is, the more moisture it can hold without the moisture becoming visible. The cooler that volume of air becomes, then the less amount of moisture that air can control. So we said before, we can take that air and we can cool it down to a point where the moisture becomes visible. In other words, the volume of air is expelling the moisture. We can collect that moisture and then take that volume of air and heat it back up. And it will then be comfortable to us temperature-wise and comfortable to us relative to the amount of moisture that's in the air. So we might do that, but we're also might just humidify it. And then we have a fan to help this process along. And then we have our air duct, which goes to various spaces, which we might consider zones of area. Now, once we've put that fresh air that's now conditioned into that space, then we have to exhaust it. And we might take that air out through a return air fan or a ductwork, but we have to exhaust it out and we just throw that back outside again. So that's the flushing system. When you say air changes per hour, that's what we're talking about. We're taking how many air changes from this space per hour do you want to change by throwing that air away and bringing fresh air back into that space, so that volume of air is what you're going to be exhausting. And how many times an hour do you want to completely flush out the space? In a highly occupied space, you might want to do it 10 or 12 times an hour. In a house, you might want to do it one time an hour or less, maybe as low as a quarter per hour. But recognize that the lower amount of times that you flush this space out, change the air in that space, the lower amount of times you do it, the less healthy that air is. There's still going to be particulates in there because we assume, and for the most part, rightly so, that the fresh air is clean and that this air is not as clean. We want to get any kind of bad stuff that's in there that one of our fellow students or workers or customers has brought in. We want to get that air right back outside. But again, generally the fresh air that's coming in is not the right temperature or the right humidity. for our level of comfort, which means that we have to cool it, heat it, maybe humidify it, maybe dehumidify it, and all of those each one of those processes requires energy in order to heat it, to cool it, to humidify it, or dehumidify it. All of those require energy. So you have a dilemma in that the more times per hour you change the air in that space, the cleaner and fresher and healthier that air is going to be. But the more times you change the air in that space, the more times you're going to have to put energy into your system in order to heat it, cool it, humidify it, or dehumidify it. So that is the trade-off. And now we as architects, after the coronavirus, the pandemic causes such a dilemma for us. We have a choice here now. Can we keep changing the air every hour? Yes, we want to because we want to make it clean. But we haven't changed the rules for the amount of energy that we can spend per square foot. The government has set an amount of energy that you can spend to heat, cool, humidify, or dehumidify a space based on the square footage of that space. Haven't changed that rule. So we can't spend any more energy to condition that air, but we have to flush the air out of that system many, many more times per hour now for the health of the occupants. And that's causing a little bit of a problem for us. You know, we have to become much more efficient with our energy. And at the same time, we have to become much less efficient with our air system. Now, if you notice here, we go back to this slide. I left a little bit early here, but we actually have a return air duct that brings that air back into, look at what's happening. We take this air out of here. We used to be able to bring some of that fresh air, some of that used air, we can bring it back and recirculate it through because this is conditioned air. This is the air that we've already made it warm enough or cool enough or humid enough or dehumid enough. And we've spent that energy. We can send some of that. We used to be able to send some of that back, actually send a lot of it back so that it would go back in and heat this or cool this other air that was coming in from the outside and then bring it again and use it. But now we can't do that, or we're not supposed to do that because that's recirculating the less than clean air back into the system, which means that we don't have this recirculation option any longer, or we're not supposed to. The healthier buildings don't anyway. So we have that real dilemma on how this is how we've done it for decades. We've sent some of that occupied air back because it's conditioned and used that energy to heat the rest or to cool the rest of the incoming air to bring it up so that there's less of a delta T. Remember, less delta T means less energy to be put in there and then recirculate that back into the space. That's frowned upon now. So we take this whole return concept air and send it right straight out. So we have a variable air volume system, which means that we change the volume of air that's going into the spaces. If we have a variable air volume system, a VAV, then the temperature is constant. We don't change the temperature of that air. The air that we are sending into these spaces is a constant temperature. We're not changing the temperature of that air up or down, higher or lower. We're changing the volume of air that's going through those spaces at a time. If we don't have a variable air system, in other words, we don't change the volume of air that goes in, it's a constant flow of air, then we change the temperature of the air. So if you have a VAV system, it's constant temperature. If you have a consistent volume of air going into the system, then you change the temperature of that air in order to modify the air that's inside of that system. Well, it's just the same. That's just the same. Right. Okay, so when we looked at that system that we have in our apartment buildings, most of the new ones are like this, in our hotel rooms, we have heating and ventilation system like this, and this would be the wall and this would be the floor. We can individually provide hot water and chilled water to our system and then circulate that tempered air into our system. Or we can have a central system that provides the hot and chilled water. So in other words, this change in temperature of the water can occur in each space by an electric unit to heat and cool, or we can do this in a central location in the building, or like I say, up at City College, they have a separate building that houses the units that heat and chill the water. And then they send that heated and chilled water to various buildings on campus. Not all buildings on campus are like that, and the newer buildings are not like that. So that would indicate to me that the central unit system that sends heat and chilled water to various buildings on the campus wasn't the most desirable method and way to do it. But this is basically, we talked about this. This is how we chill and heat the air. It could be chilled and heated in each space, or it could be chilled and heated in a remote space and sent to each of the spaces. And then we can run the air across it in order to get that chilled air or that heated air. And this is where we have the outside air. And again, we're going to have the louver and the filter. And then we'll bring that outside air in and condition it and then circulate it through the room and then exhaust that conditioned air someplace else and bring in more air from outside into the system. The more fresh air we bring in, the healthier this air in theory would be inside the space. And the more fresh air we bring in, the more conditioning we have to do. And we know that conditioning costs energy, and we're trying to do both things at the same time. Make the air in the spaces as healthy as possible and uses the least amount of energy, and they're conflicting goals that they don't correspond with each other. Okay, so we have to filter that air out. We know that the outside air has particulates in it that we don't want to be introduced into the space. So we use what's called a filter, and you all know about that from your experience. You have filters attached to your faucets sometimes, which filter the particulates out of the water. You have filters in your heating system, where if you have a forced air system, you have the air flowing across the filter. As that air flows across the filter, what happens? It grabs and holds the particulates. And the more that filter is able to grab and hold, the more resistance there is for the air getting through from one side of that filter to the other. And we know that we need to create a movement of air, But if you put something in there that resists that flow of air, that then you're going to have to add more energy to your system, probably in the way of a fan, a higher horsepower fan, which consumes more energy in order to push that air past that blockade, which is your filter. So again, we have this conflicting amount of desires here. We want to use less energy to push the air, but we have to use more energy to push the air when we have a good quality filter that grabs and holds that particulates, because that's slowing down. And you know that if you have a wide open hole in the wall and you're trying to blow air through it, you know, there's not going to be as much resistance as if you put a very fine filter or screen across there and then try to blow air across it. You know, there's a resistance there. That resistance has to be overcome by increasing the flow of air, which we know translates into additional costs because we're using more energy.
So, Professor, in
Yes.
that case, wouldn't changing the filter frequently help
Yes,
to lessen the amount of electricity?
absolutely would help, because as the filter grabs and holds, it's making the openings where the air can actually go through smaller and smaller. You're absolutely right. So changing the filter more often is a good way to make sure that you aren't resisting the flow of air. But again, that costs money too, you know, to make those
Yes.
filters. And now we have electrostatic filters, which you know how static electricity works. You know, you take the balloon, you rub it on your head, and you put it on the wall, and it stays there. That's static electricity. Well, what we have are electrostatic filters, which are charging the air, which then charges those particulates. This is inside of the furnace flow of air anyway. And then there's a metal plate that the statically charged particulates hit upon. And then you can wash those particulates off with a schedule of flow of water that runs across that flat plate and then is collected and sent off to the sanitary sewage system, and it collects those filters. It sounds like if you ever been in somebody's backyard that has a bug zapper, and it sounds exactly like that when the electrostatic charge goes into the particulates hit that plate, and they make the same noise that you hear when the bugs hit the bug zappers light fixtures outside of the house on the porch. Makes that exact same noise. You know, it's a zapping sound. But that's a good method, because now you don't have to change the filters. What you have to do is just schedule, you know, you can schedule that flow of water across that plate that has grabbed all of those particulates and flush them away. It's a much better way, except that not all of the electrified particulates attached to the plate. Some are recirculated back into the house, and then now they're charged, and they're dirt essentially, and they attach themselves to the wall and attach themselves to the wall. And over time, you have an electrostatic charged bunch of dust particulates that are up against the wall. Now you have to clean that wall. But it does make sense, and I think, Lisa, that makes me feel good that you're understanding the concept of the filter by saying, well, you know, the filter is grabbing this stuff. It's going to make the holes that the air goes through even smaller because the particulates are on it. So it makes sense to take that filter out and put a fresh one back in. And yes, it would. And your system works much better much more efficiently when the filters have really big holes in it, but then they don't grab as much particulates. So they work really much better to grab the particulates when they have really small holes in them. And that reduces the flow of air, which means you have to increase the energy into the fan in order to increase the flow of air to get through the filters. So let's just talk about the HEPA filters. You know, your Tesla car has a HEPA filter in it. That's got the very, very high efficiency filters, but those little holes in the filters are really, really, really small. I know that Elon Musk has said more than once, he said, if there's any sort of a chemical or biological attack, that's you want to go jump into your HEPA filtered Tesla because they have those really high quality filters. And so a lot of the vacuum cleaners also talk about having the HEPA filter, but it's 99% efficient, which means that it's going to grab 99% of the particulates that come across it, which means what? That those little holes in there to begin with are going to become even smaller, which means that we're going to spend more energy to push the air through those smaller and smaller holes. So how do we move the air that we want to push through those filters? Well, we have two different types of fans. One is an axial fan and one is a centrifugal fan. Now, an axial fan, you've seen them, you might even have one, but you go to the big box stores, you see them in the grocery stores too. They're just a metal frame with a grid on both sides and a fan in the middle. It's like a airplane propeller. It's just a axial, it's like a fan inside of a box. That's your axial fan, and that's how that throws the air. And the other is a centrifugal or a squirrel cage, which you might or might not have seen those as well, but they just suck the air in as that squirrel cage spins around and then pushes the air out. Both we're trying to use those in order to do what? Get the air flowing across there. What kind of ducts when we have, now we're working with pipe. We're putting hot water through the piping system. But when we use air, we have different types of materials for those ductwork. And I'm 71 years old. I've never seen a wooden duct, but Dr. Edwards said that ducts can be made out of wood or fiberglass or stainless steel, and I believe him. Although I've never seen one that would be just it's an enclosure, could be rectangular or round to get the air to go in an area that you want it to go into. So let's talk about the sizing of the duct work now. Now, the relationship between the horizontal dimension and the vertical dimension, if we're talking about a rectangular duct, for efficiency purposes, should not be greater than 4:1 or 1:4. So in other words, if you took a look at the dimensions of the ductwork, neither of those should be greater than 4 times, should not be greater than 4 times the other dimension. So if it's 10 by 10, 10 inches in horizontal, 10 inches in vertical, then neither one are greater than the other one, so that would be fine. But if one were 3 inches and the other were 10 inches, that would be greater than a 4:1 relationship, and that would not be efficient. So that's what we're saying is, as we're going to quickly design a duct size, and then you want to double check it just to make sure that it stays within that ratio, so that the longer side is not greater than 4 times the shorter side. So we measure airflow in cubic feet per minute, CFM. And if we know the airflow in CFM and the velocity in feet per minute, we can calculate the cubic feet per minute requirements or the duct size requirements. And we would simply say that the area of the duct is 144, which is 12 times 12. So we're taking square feet and turning it into square inches. So 1 square feet equals 144 square inches. And Q is the airflow in CFM divided by the velocity, which is in feet per minute. And that's going to tell us the area of the size of the ductwork that we need. So in Dr. Edwards' example, he told us we have 800 CFM, cubic feet per minute, and we have a velocity of airflow of 1,000 feet per minute. What's the size of the duct? Well, here's our formula, 144 times Q divided by V. Q is 800, V is 1,000. So 144 times 800 divided by 1,000 equals 115 square inches. So now we want to discuss an area of the ductwork that would satisfy 115 square inches of area, which would be 12 by 10 would be very satisfactory. That would be 120 square inches. And so we know that 120 square inches is greater than 115, so that's good. Let's double check it for, is either size 4 times bigger than the other? No. So that's an acceptable size of ductwork. All right, so let's talk about our air changes per hour because we've done that before. We need to do it again. So if we said we have a 20 by 20 by 10, so that's length times width times height, that's going to give us volume because volume is in cubic feet, and that's feet times feet times feet would be cubic feet or feet squared. And we have, that's the volume of the area. We have 600 cubic feet per minute of conditioned air. How many air changes per hour are required? Okay, the number of times per hour that the air volume within a space is exhausted or respaced. That's your air changes per hour. Okay, so let's say we got our room volume, we know that. And our CFM, cubic feet per minute, is 600. 600 cubic feet per minute. So air changes per hour is 600 cubic feet per minute times the 60 minutes in an hour. So we're going to multiply that times 60 divided by V, which we said was the volume, which is 4,000 cubic feet. So how many cubic feet per minute of air do we need? We need 9 air changes per hour. Why is that air changes per hour? Because it's air changes per hour equals CFM times 60 divided by the volume. We've given the CFM of 600. Where 60 is 60 minutes in an hour, and the volume we knew was 20 by 20 by 10. That just, in order to come up with air changes per hour, we take CFM times 60 divided by the volume. Okay, so I think you're going to see some of that on your you'll definitely see that on your midterm. What's the air changes per hour? Just make sure to convert cubic feet per minute to cubic feet per hour. How do we do that? We multiply it times 60. Then we have our cubic feet, and we divide that by our volume, and that will tell us how many air changes per hour we need to have.
What is the CFT?
CFM.
That says
CFM is
room
cubic
volume
per
V
minute.
equals.
So
No, it's on the room volume V equals 20 by 20 by 10 equals 4,000 CFT. Is that supposed to say CFM or is that?
yeah, cubic feet is what it really is.
Okay, I got you.
Yeah, but a good question, because if you have a question about that, I'm sure other people do too. But 20 feet by 20 feet by 10 feet is 4,000 cubic feet. That makes sense.
Yes.
4 feet
Yes.
cube. Okay, that's where the volume.
Thank you.
And if you're changing the air for 4,000 cubic feet per hour, then you have 1 air change per hour. Okay. All right, so the exam should open up. We have a couple minutes left for attendance, and we also have a couple minutes left for questions. So let's do the attendance first. Let's start with, today's the 28th. Yep, okay, let's start with Gabrielle. Let's go to Zanetta.
Here.
Whoops, I did that exactly backwards. All right, let's take about Jason. Duran,
Here.
all right. Dratero,
I'm here.
that's a good two. David,
Here.
all right. Fahim,
I'm here.
Jonathan,
I'm here.
Eli, Kojo.
I'm here.
I thought I saw you come in there. Yeah, Carlos. Yakuba. Jeffrey.
Here.
Ty. Adil. Khan.
Here, Professor. I'm here.
Lisa, I know you're here.
I'm
Adam.
here.
Yeah.
I'm here, Professor.
Who
Good
just
morning.
said that?
Adam.
Did I get you or not, Adam? Yes, I did.
Yes.
Okay. Yep. Nader. Steven.
I'm here.
Willen. And Amir. And Alter, I saw you come in, so I know. Okay, so that's good for the attendance. The other thing is, if you have any questions about the project, we can talk about that for a couple minutes. I know Lisa came in to either office hours or a private Zoom meeting. We went over her numbers, and she was very concerned that her BTU numbers were really, really high. And we went through one by one by one, and we noticed that she had failed to put in any kind of insulation in her ceiling. And so therefore, there was a tremendous heat loss. And we talked about, what if you put 6 inches of fiberglass in your ceiling? What if you put 12 inches? What if you put 18 or 24 in the ceiling area? So those are the materials you want to put in, are your gypsum board and some sort of fiberglass insulation. And that brought her numbers down substantially. So what that tells you is you do want to insulate your ceiling. We all know that from experience in the profession, but your spreadsheet is going to share that. And that brought her numbers down very good, a very good location of her numbers in terms of the range of what's acceptable. But does anybody else have any questions about the project? All right, I did record this. I'll post it and I'll put the link there, and I will see everybody. I think next week we do have a class, right, on the 4th? I believe we do. And the 4th is remote. So see everybody next week in front of the computer. The midterm should be open up in a couple minutes, and if it's not, text me right away, let me know. I'll see everybody next week, same place, remotely.
Professor, for the midterm, we have one attempt, right?
I think so, but I don't know, because I'm not sure how to set that up to let you do more than one. If you try to do it in parts and you have a problem, then just let me know. Send me a text message and I'll try to open it back up for you.
Okay, thank you.
So,
Okay.
Professor, that would be the same format, right? It's submitted next week by 10 a.m.
Yes. Well, yes, by
Okay.
10 a.m. Yep, you're right.
Okay. All right. Thank you.
Okay, Lisa.
Thank you, Professor.
All right. Bye-bye, everybody.